Hey, what's up everyone? In this video, we're going to solve integrals using trigonometric substitution. So there are three formulas that you need to know. So when you see something like this, when you see that there is a square root of a squared minus x squared in your integral, you're going to let x equal to a times sine of theta. And don't worry, I'm going to show you plenty of examples. If you see the square root of a squared plus x squared, then use x equals a times the tangent of theta. And the last one is the square root of x squared minus a squared. In this case, you have to use x equals a times secant of theta. So let's say we're using the first form. Well, our assumption is that theta is between negative pi over 2 to positive pi over 2, and so on. But don't worry too much about this. These are the ones that you need to know. Our first example will be the integral of the square root of 9 minus x squared over x squared dx. So right away, we see that we have 9 minus x squared. And 9 minus x squared is the same as 3 to the power of 2 minus x to the power of 2. So which form do we have? Is it the first one, second one, or third one? Well, you guessed it, it is going to be the first one, and you can see that a is equal to 3. So our formula will be x equals a times sine. So x equals a, which is 3, times sine of theta. And we also need to find the derivative. So the derivative dx over d theta, what is the derivative of 3 of sine? Well, it's going to be 3 times cosine. And what we can do is multiply both sides with d theta. So let's do that. And we end up with dx equals 3 cosine d theta. So we have the integral of 9 minus x squared. And x is 3 sine. So 3 sine to the power of 2 over x squared. So the same thing. 3 sine to the power of 2. And don't forget the dx. This is very important. So dx is equal to 3 cosine d theta. So 3 cosine d theta. I'm going to put x equals 3 sine up here because this is something that we will reuse later on. Now, what is 3 sine to the power of 2? Well, it's going to be 9 times sine of theta to the power of 2. So 9 of sine theta to the power of 2. Now let's simplify the numerator as well. So we get 9 minus, and this will give us 9 sine of theta to the power of 2. And we need to factor out the 9. So we get the square root of 9 times 1 minus sine of theta to the power of 2. Now we can still keep simplifying this using our trigonometry identities that you might have learned in high school. So those ones are cosine of x, and this is to the power of 2, plus sine of x to the power of 2 is equal to 1. You also have tan of x to the power of 2 plus 1 is equal to secant of x to the power of 2. And the last one is cotangent of x squared plus 1 is equal to cosecant of x to the power of 2. Now let's take a look at this one. If you subtract sine x squared on both sides, let's do that. You will get cosine of x squared is equal to 1 minus sine of x squared. So we need to replace this part with cosine of x squared. And notice that we are using theta instead of x because we have been using theta all along. So here we have to use theta. And what is the square root of 9 times cosine to the power of 2? Well, that one is easy. That's going to be 3 times cosine. So let's replace the numerator with this one. Let's go ahead and multiply 3 cosine with 3 cosine over here. So we will get 9 cosine to the power of 2. And here the 9 and this 9 will cancel out. So what is this going to be? We know that tan is equal to sine over cosine. How about cotangent? Well, cotangent is 1 over tan. This is the same as 1 over sine over cosine, which is the same as cosine over sine. So here we have cosine to the power of 2 over sine to the power of 2, and this whole thing is equal to cotangent to the power of 2. So how can we solve the integral of cotangent to the power of 2? Let me show you an easy trick. So you can see here this diagram, we have secant of x and this arrow to secant of x and this arrow pointing backwards with the 2, then tan of x, and the same thing over here. The difference here is we have cosecant of x points to negative cosecant of x, and then we have this same arrow and then cotangent of x. So how can we use this diagram? Well, let me show you. So the derivative of tan of x is equal to what? We see this arrow, right? So we have secant of x, and then we have to the power of 2. And we go this way, right? And then we get blocked up by this arrow. So that's kind of the way that I do it. When I look at tan, then I see secant of x. So that's how I get this one. And similarly, how about d over dx of cotangent of x? Well, same thing. I look here, then I go over here, then I see cosecant. So negative cosecant actually. And then don't forget the to the power of 2. How about the derivative of secant of x? Well, when you're going on this side, what I want you to do is actually to erase these two arrows. So the derivative of secant of x, you get secant of x, tan of x. Because here we see secant of x, then tan of x. Then the derivative of cosecant of x is equal to negative cosecant of x. So negative cosecant of x times cotangent of x. So this is a very neat trick. And don't worry, you will see why we need this in a second. Let's go ahead and erase everything except for this part. So let's erase everything. There's actually no direct way to solve the integral of cotangent to the power of 2, but there is an indirect way. So the indirect way is to convert the cotangent to the power of 2 to a cosecant. So if we look at our trigonometry identity and subtract both sides with 1, we have cotangent to the power of 2 is cosecant squared minus 1. And let's go ahead and split this integral apart. So we have the integral of cosecant to the power of 2 minus the integral of just 1 d theta. Now, 1 d theta, what is the antiderivative of this? Well, the antiderivative of this is just theta plus c. Since the derivative of cotangent is negative cosecant squared, then we know that the integral of cosecant squared is going to be negative cotangent c. It's like saying, well, you have the derivative of cosine, and that gives you negative sine. This means that if you do the integral of sine, so this means the integral of sine is going to be negative cosine. So the same logic applies here. And we're almost done. So remember the x equals 3 times sine of theta. This is where it comes in. From this, we know that sine is x over 3. And if you take a look at our triangle, this corner here is theta, then we have the SOHCAHTOA rule. So the SOH rule says that sine is equal to opposite over hypotenuse. And our opposite will be the x, and the hypotenuse will be the 3. So our opposite will be x, and our hypotenuse will be 3. We just need to find this side. The Pythagorean theorem says x squared plus b squared is equal to 3 squared. So this means b squared is 3 squared minus x squared, and 3 squared is 9. So b is equal to the square root of 9 minus x squared. Now you might be wondering, why is there no plus minus sign in here? Well, that's because the length of the triangle is always positive. That's why we only want the plus, we don't want the minus, and it's just redundant to write it at all. And let's replace the b with 9 minus x squared. Using this triangle, we can find the cotangent. So cotangent is equal to 1 over tan. And from the SOHCAHTOA, tan is opposite over adjacent. So opposite is x, the adjacent is the square root of 9 minus x squared. So this would be the square root of 9 minus x squared over x. And what is theta going to be? We know that sine is x over 3, so theta is arcsine of x over 3. And this right here is our antiderivative.